Hello there, my name is Alexei, and I will tell you about the code generation for John Ripper, John Def Key. This is the specialized code generator, which. So, John Def Key is the experimental code generator. It's kind of a global experiment. The results of it have not yet been integrated into John the Reaper. At the entry, this code generator gets the description of the algorithm in a specific language and also the file with the settings of how to optimize that algorithm. In the end, we get to see the pure seed for John the Reaper. John the Reaper is a well-known hash creator. It's even been mentioned in the previous presentation. And its main objective is to search for weak passwords in the Unix systems. However, it also supports over 200 different formats of hash, types of hash in Jumbo. This is the community enhanced version. Also, it supports the work on different computational devices such as processors, video cards, with the GPU and FPGA, the programmable hardware such as Bifani and so on. The development of such format causes certain problems because when there is optimization, it must be applied to all the formats, and certain optimizations are hard to be applied to certain formats when there are no common bases in the code. That's why first we optimize the more important formats, and certain formats remain unoptimized. Also, there's a support for every device on which John works, and it requires a specific format, a separate format. That's a different iteration. That's why certain optimizations, such as vectorization and OpenMP support, uses macros in the code, so they load the processor, decreasing the readability of the code. The objective of the John Dev Kit is to separate the algorithm optimization and the code to generate the code for different devices. So John Dev Kit also must include different optimizations for hash creating and John the Reaper. Give the more convenient syntaxes, not to slow down the speed, and give the precise control over optimization. Support different kind of computational devices and provide a good, perfect generation output for perfect input. A very well tracked form and very well prepared for John Dev Kit must give a good code, must output a good code. John Dev Kit does not try to make good code out of bad in every case. Also, John Dev Kit tries to be more simple. We have already got the results here, and while John Dev Kit cannot be considered now to be a mature project yet, we have 7 formats realized, and they have separate code, their optimization, and the output. The SHA-2 system got the boost, the speed boost, and other formats have slowed down. We'll fix that. However, they use some interesting features which I'm going to tell about in more detail later. Optimization is done with the interleaf. There is automatic vectorization, the unroll cycles, the early rejection of the bad candidates with wrong hash, and additional use of bigger packages. So the cycle around the algorithm is getting bigger. All the formats got the optimization just with by clicking in a config. I'll tell you about the process of selecting the hash. We are in this position of the attacker, and we have a lot of candidates to check. So that's why this is the parallel work. It's always present. We don't need the algorithm to be parallel or non-parallel. It's always parallel. And the general view of simplification, we can imagine the cracking algorithm as the load of hash and generation of certain set of candidates, the computation of the hash from them, or partial computation of the hash, the rejection of the non-probable candidates with low probability or zero probability, and then the more precise check. We do the more precise check of the possible candidates which actually can be the passwords. After that, we repeat the process with the generation of the candidates, and John uses the interface to describe the formats that reminds the object-oriented interface thanks to callbacks. Certain optimization is not specific for the algorithms and does not touch them in any way, such as the support of OpenMP and the increase of the candidate package. Other optimizations are tightly interact with the algorithms. That kind of optimizations include vectorization, the calculation of the preliminary calculation of a certain part. If we have certain parts repeating in the passwords, then we can compute certain operations in advance because certain operations are unchanged. Also, the addresses, the calls to the operations, the loops, interleaves, bit slicing, and other optimizations. Bit slice requires a separate attention because it separates the candidates into bits and treats bits like via bit operations. In the meantime, bits are put into the better type that we have, but we get vectorization to 64, 128, or 512 vectorization on OxygenP. That's besides the optimizations are actually the optimization of Hawkwitz or Billowit formulas. That has a huge background for a very large scale degradative circuits. For John the Ripper, Roman Rusakov has generated the following formulas just by going through them. That took about 3 months, and after that, Solar Designer improved the scheduling instructions, and that formulas are being used now. They're generated by the software. Billy Bob Brumley showed the use of artificial burning to improve the scheduling of the instructions into the boxes. In addition, the instructions were connected to the processor, and that gave the 10% boost. So we can say that the generation of the code, including the advanced algorithms, is not something new for John the Reaper. When I start talking about the output for different platforms, I'm often asked, well, there's OpenCL. What's with it? What's so bad about it? Well, let's start with the fact that the syntax is very heavy. Its C syntax is very heavy, and John DevKit provides a simpler syntax. Also, OpenCL compiler doesn't know anything about John the Reaper, and it cannot transfer the code between the functions in the format. And also, it doesn't have any automated bit slicers. Automatic bit slice is generally a very rare optimization.
Now, John does have dynamic formats. It's a mechanism that allows you to combine cryptographic primitives to get some different kinds of hashes, MD5 of this password, and they use the same base of source codes, and they do not repeat. MD5 of MD5 of MD5 is one piece of code, not two big ones. John DevKit intends to do the same during compilation, getting more of the code, but with the possibility to optimize. If we calculate MD5 from MD5, for the second MD5, we always know the length because the results of the first MD5 always have a fixed length. In C, there are macros, and they're used a lot in John and other projects, giving great opportunities, but they are not that sophisticated. This is an example of code from algorithm Ketchak, and they use unroll algorithm with the different pieces of codes. The X macro technique is also interesting. When part of the code is put into a separate file, and before including this file, variables are defined, and the file can be used as a template. I saw that in encrypt and NetBSD. So, and this is when maxc is included. And the full route from definition to C in John looks like this. From algorithm definition, you get the intermediate representation, intermediate language, which is modified with filters, user-defined filters. That is, the user will definitely control all the changes that happen with the code. The compiler does not do anything itself. After that, you get the C code. This intermediate representation is needed to simplify what you do with the code. Algorithms are described in clean Python, but the representation is very simple, and it's actually a mass of instructions. The instructions are very simple with just a few arguments and one result. So the intermediate language has instructions for algorithmic hashing, like one which describes the variable state of the function, which is used in some filters. This use of special instructions for different structures makes optimization easier, because the optimizer does not have to build structures, but is taking those which are ready. This is an example of a specific instruction and an example of the code and the use. SHA 224 is different from 256 in two ways. It's different. They're different in terms of initial state, and one output is also reduced. So all the work with the bytecode can be a very small function. Now about optimization, which is specific to password cracking and specific to John the Ripper. We as compiler users have knowledge that conventional compiler does not have. We can move code between functions, and we can use knowledge about the probability of functions to be called. The main hashing function is always used, but the function of precise check or verification is not always used, but only for candidates who are passwords with very high degree of probability. And with this we can calculate the main functions, not the whole hash. Hash is long, have a number of meanings. We are happy with one, 32 or 46 bit. So from the main function we take away those operations that we do not need for calculation. The whole code that is used for the rest of the calculation is taken out, but we lose the possibility for precise hash verification. then we need to, if we need to do that, we have to calculate hash again. It's an expensive operation, but it's so rare, it's so rarely used, we can disregard it. And this implementation will be scalable. To implement such optimization, we need to have two implementations, the vector and scalar, for verification. It's not easy to do manually, but John DevKit automates that. Both for both vector and scalar optimizations use the same algorithm description. One interesting optimization is reversal of operations like addition. When we see that int in the hash was obtained by application of constant, we can deduct the constant and see the state with one operation earlier. It's once for hash, not once for candidate. There are not as many hashes as candidates. It's a benefit, but we need to move codes to known places, so it should be a reverse code with other instructions, and John DevKit does that. In John DevKit, we can use full Python. We did not turn Python into a language, but we implemented a domain-specific language within the Python using objects with overloaded operations. In this way we can apply precise control, and in some cases we can use all the power of Python to get the byte code. But this is always calculated before bytecode and before optimization starts. So in well-mapped formats you will not need to do that. This is an example of MD4 code, which compiles the code very quickly from RFC and is described as two numbers in brackets. So it's calculated within the format. It's also then disclosed into a separate instruction and optimizes in a decent C language without a function. So we can conclude from that John DevKit demonstrates how you can practically apply code generation, because code generation is something which is very general. You cannot always know if it will be useful, but additionally John DevKit appears to be a practical optimization solution, because you can do optimization once and then apply it to all algorithms which are described for it. Thank you. Questions, please. Did you apply your software product only to hashes that you showed on the slide, H and MD5? What about Russian-made standards? Not yet, but we will do that definitely, because John does support Trebug. It was added just a week ago when hash runner PhD test was done, and we will automate that. You were showing implementations with John DevKit, taking standard algorithms. As for applications, algorithms which use MD5 within it, this is something you can write in Python and compile it into C. Is that right? Yes, potentially so. And with that, John-specific optimization will not be available, because you will not achieve it in parallel Because I think what you are asking for is one candidate one time, but not in packages of thousands. On the other hand, we started with generation code for hash computation without John. And the types which I use now are more or less disassociated from John. You can separate the kid from John. Thank you for your questions.